Okay, what we know about flow lines so far is that if we have a really good vector field graph, we can maybe sketch the flow line pretty well. We can find the flow line almost exactly as long as we actually recognize what it is in advance and then try to find parametric equations for it. It doesn't sound likely that that's actually be possible very often. There's another method that gets used a lot more often. This is new numerically. This is a method called Euler's method, which you see at the end of Calc 2 and the end of Calc 1. The idea is if you want to change in a function value, you just write down the following equation. I want to change in a function value. That's exactly equal to delta y over delta x times delta x. And as long as delta x is really, really small, delta y over delta x is actually very, very close to dy dx. So you get something like this. So it says you can estimate the change in a function value as long as you know the derivative and a small value of a change in x. And what Euler's method does, it just allows us to make a giant, huge table that works very, very quickly if you use something like a spreadsheet. Meanwhile, I'll show you how you might do that here. What we want to do is pick any starting point that we want. I'm going to pick something that's nice and easy because I'm going to have to do most of these calculations in my head. I want to start at the point P11, and what we're going to do is make a giant table. Now, velocities are involved here, so I have to have a t. We're going to have an x-coordinates. Give myself a little room just in case there's some decimal places. I'm hoping not. A little room for this. And what we want here is we want the change in x. Well, using Euler's method, that should be just about dx dt times delta t. And notice here, by the way, remember how this works, is that if this is a velocity field, then the I component is dx dt. So if I want this here, I'm going to write down minus y, because that's dx dt here, times delta t. And I'm going to do something similar for dy. I want the change in y is approximately equal to dy dt times delta t. And if this is a velocity field, then the j component is dy dt. So this would be x delta t, like that. Try to squish over here. Now, whenever you do Euler's method, you need to pick a starting point, and I already did. You need to pick a delta t that you're happy with. I'm going to pick a delta t of 0.1, which will show up in the second line. Actually, I'm going to regret putting this line here, but here we go. I want the delta t to be 0.1, so I'm going to go like that. I'm going to calculate my change in x. My change in x, according to this, is minus my y value, so that's going to be minus 1 here, times the delta t I chose ahead of time, so that's 0.1. So I'm going to get minus 0.1 for my change in x. My delta y is going to be my x coordinate times my delta t, which we decided on ahead of time, and so I'm going to get 0.1. Now what do we do with these? I'm going to go to my second line. My new x value is going to be my old x value plus how much it changed. So that's going to be 1 minus 0.1, that's just going to be 0.9. My new y value right here is going to be my old y value plus how much it changed, and that's going to take me up to 1.1. Now what happens next? We just do it again, right? The change in x is minus the y value, so in this case it's going to be minus 1.1 times delta t, which is 0.1, and so this is going to be minus 0.11, like that. My delta y is going to be my x, which is 0.9 here, times 0.1, and I'm going to get 0.09, like that. And what happens? Well, no one said to stop, so we keep going. My new x value is going to be my old x value plus how much it changed, so this is going to be something like 0.79. My new y value is going to be my old y value plus how much it changed, and that's going up to 1.19. And you can see, you can just keep going on, right? And if you're doing a spreadsheet, this just drags down beautifully. Now, one word of warning, if delta t isn't very small, then this approximation isn't very good, and these points move very, very far away from the real flow line very quickly. Even if delta t is tiny, because each one of these is an approximation, and then we're using those in our next calculation, you're going to start veering away from the flow line. But you can, and for short term, make good progress on what the flow line might look like. We now have 3 points on the flow line that we could connect up and see what's happening. One final note, when they study stuff like global warming, Euler's method is one of the first things. It's one of the very basic things at the bottom of the whole calculation. But you can see, without second derivatives, right, you fly off the actual thing very quickly. All right, that's all there is for Euler's method.